So we started oscillations and waves. The first video that you watched was a quick little demonstration, the simplest example of an oscillation, where we have a mass on a spring. That mass is going to vibrate at a certain frequency. And we define frequency as 1 over the period. What this tells us is how many cycles are happening every second. The period is another way of saying seconds per cycle. This is incredibly important for everything that we do from here on out, that you understand that there's going to be a relationship between simple harmonic motion and circular motion. Okay? So basically, it's how many times we're completing a motion that's being repeated. All right? And that motion that's being repeated, it could be anything. It could be a mass in a spring, a pendulum, like a swing, objects bobbing up and down in water, a musical instrument. Any sort of vibration like that is an oscillation where the motion is repetitive. It comes back to the position it started at, and you can count that as one cycle. Now, there's another term here, angular frequency, that you guys are going to need to know. An angular frequency is given by the symbol lowercase omega, all right? And what angular frequency is how many radians are being completed every second. So we know that in one cycle, we go through 2 pi radians. So one cycle, with there being 2 pi radians, okay, angular frequency is just going to tell us the number of radians per second. In other words, how do we get that? 2 pi radians per cycle. The frequency is normally going to be a cycle per second. Cycles cancel out, and we're left with radians per second. And we actually just report this like this, because radians are not a unit. Hopefully you remember that from math class. One extra thing I want to mention really quickly from the previous slide here. Okay, when we talk about frequency, hopefully you talked about frequency when you talked about circular motion, but the unit for this guy, cycles per second, this is what's known as hertz. Hz. Okay? Remember, radians are not a unit because they're just a measure of the ratio of 2 sides of a triangle. All right? Or pardon me, the side of a triangle and the arc length. I take that back, the arc length of a circle, I believe. I forget exactly, but I know that it's basically 2 lengths that cancel each other out, and therefore it's unitless. Okay, so let's continue here. For angular frequency, there's one other way of looking at this. Don't forget, frequency is just equal to 1 over the period. So we can rewrite this as the angular frequency is equal to 2 pi all over the period. And we will sometimes use that as well. All right? So the example that I give there, a pendulum completes 10 swings in 8 seconds, calculate its period. The way to do that is 10 cycles for every 0.0 seconds here. Okay? So, should take that back, excuse me. Whoops. 8 seconds divided by 10 swings, there we go, 0.80. And I'm going to put a decimal here, I'm going to give that 2 sig figs, change it, okay? The frequency is equal to 1 all over the period, 1.25 hertz, and that should be 1.3 hertz with sig figs. All right, so that's the frequency that they asked us to solve for. That means every second, 1.3 cycles of this pendulum swing back and forth are completed. And the angular frequency, right, omega is equal to 2 times pi times f. What this tells us, all right, 7.8, and we write this not as radians per second, but just, you know, radians is implied, so we would say it as radians per second, but we write it as per second. This tells us that 7.8 radians of angle are swept out every second in terms of if we're imagining this cycle on a circle, okay, going around like a unit circle. Very, very connected to the unit circle you guys remember from trig. We will be talking about trig functions here in a little bit. All right. A restoring force. You have a definition there. Restoring force is a force that tends to restore the system to its equilibrium motion. Therefore, it is, all right, what you need to know. In general, the force directed opposite the displacement. What does that mean? Well, if you go back to my mass in a spring example, okay, and we have this spring, it's unstretched, all right, and then we take that same spring and we stretch it out because we have a mass on the end of it. The force, if we look here, this is 0, this is x naught, we'll call it, right, the amplitude. That spring has been stretched this way. Which way is the force from the spring pulling? Well, the force in the spring is pulling up. That's what this means. The force is directed opposite the displacement, okay? So the force from a spring, the equation that we use for this is Fs is equal to negative kx, all right? Where x is the displacement and k is what we'll call the spring constant. And this tells us how stiff the spring is. So if the spring is stiffer, you're going to need more force, and they're directly proportional. No big surprises there. All right, let's take a look at simple harmonic motion, or mass in a spring, and exactly what's happening with the displacement velocity, the restoring force, okay, and the acceleration. All right, so we've defined a restoring force for the sake of looking at this example here to know that this object stays in its vibration, it's oscillating because something is pulling it back the other way. That's the restoring force I mentioned in this previous slide here. So over here, the displacement in the first position is at a maximum. We see it's at the amplitude, and we know the amplitude is the maximum displacement. So we're going to write at a max here. What is the velocity at this point? Well, if you go back and look at the video, you'll see that at the top and bottom of the motion of the mass in the spring, it pauses for a second. So the velocity is 0 there. The restoring force, since it's stretched to its maximum displacement, is also going to be at a max. And since force is directly proportional to the acceleration, we're also going to assume that is at a maximum. I think you're going to see a pattern emerge here, okay? At position 2, displacement is equal to 0. That is when the velocity is going to be a max, actually, when it's passing back through that point. If you watch the video, again, of the mass in the spring, you see that's when the mass is moving the fastest, when it's moving through the center, its equilibrium position. Okay? The restoring force is 0 since the spring is not stretched, and therefore the acceleration is equal to 0. We're going to see this pattern happen again for 3 and 4 for the exact same reasons. All right? So when is its velocity, okay, of the mass at its maximum value? Well, v is at a max when x is equal to 0. When is the acceleration at a maximum value? Acceleration is at a max when the position is at its largest, is at the displacement. Okay? So at which position is the mass in equilibrium? Well, the mass ends up being in equilibrium, okay, when x is equal to 0, because net force at that point is equal to 0. There are no forces acting on it. Again, we're ignoring gravity here. We're only considering the direction of motion. This is like on a horizontal surface, okay? So we're only considering the direction of motion where the spring force is acting on it and no other friction, okay? So, here we go. The official definition of simple harmonic motion. We have oscillations, okay? We have motion that takes place. We have motion happening where the object is moving up and down, and the acceleration is constantly changing. All right? But our official definition of simple harmonic motion is motion that takes place when the acceleration of an object is proportional to its displacement from the equilibrium position and is always directed back towards its equilibrium position. That's a really important definition. Okay? What that second part tells us, the acceleration is in the opposite direction of the displacement. It's a big point, okay? In addition to the acceleration and displacement being proportional. How do we show that? Well, the net force acting on that mass is only the spring force, which is equal to negative kx. Net force is equal to mass times acceleration, which is equal to negative kx. And if we solve for a, we see it's equal to negative k over m times x. What we see here is exactly the definition of simple harmonic motion. Okay? What we see is that A is directly proportional to negative x. The other way that we define this, and we will come across this later, is that A is equal to negative omega squared times x. This is the third way you want to see it, okay? These two are the actual mathematical relationships we'll be using. The graph, therefore, looks like this, okay? It goes through the origin. That's the directly proportional part. And the slope is negative. In fact, the slope is equal to negative k over m, or negative omega squared. I will show you this equation right here. We will derive this in a little bit, but I want to show it to you at least right now. So that's it. Simple harmonic motion is motion that satisfies these conditions. Those conditions are provided by a restoring force. And yeah, you've seen some of the basics here. We're going to get into the trig and describing this motion in the next video.